5.2. Again, this section is pretty straightforward. It's just a notation, and it's important information. You'll use it as you move forward in calculus. Okay, so section 5.2 called sigma notation. Why are y'all moaning? Okay. Okay, so you have this weird looking E thing. It's really ugly. Okay, and that symbol is called sigma. It's the sigma symbol. Okay, and this is a Greek word, Greek symbol. It looks Greek, doesn't it? It looks like something you'd expect the Egyptians to be using. And then you have k equaling 1 to n. And these are called your index. This is your index beginning. Index begins. And the n is where your index ends. Okay. And then you'll have usually a little formula sitting here. Here they do a sub k. So this sigma symbol is also referred to as summation, which means you're going to sum some terms, meaning you're going to add some terms together. And so let me show you what this really turns out to equal. What this equals is if you had an example where you had sigma of k equaling 1 to 5 of a sub k, this is equal to a sum. And the sum is where you start with k being 1, then k is 2, then k is 3, then k is 4, and the last number k can be is 5. So then you have a where k is 1, plus a where k is 2, a where k is 3, a where k is 4, and a where k is 5. So you plug in, increments of 1, k is 1, k is 2, k is 3, k is 4, k is 5, and you add these terms or you sum these terms together. So when you actually look at some examples, if you took, if you've done sequences in series in pre-cal, then this will come very quickly to you and very easily. If you have the summation of k equaling 1 to 5 of, well, they say k. That's kind of strange. We can do that. Yeah, that's okay. Then this would be 1, k is 1, plus k is 2, plus k is 3, plus k is 4, plus k is 5. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. Now, if you want alternating signs, so one is positive, one is negative, one is positive, one is negative, then you could have an example like this. The summation of k equaling 1 to 3 of sig negative 1 to the k times k. When you get the negative 1 to the k, that's what's going to give you the alternating positive, negative, positive, negative, positive, or negative, positive, alternating signs. So your first one is to plug in a k value of 1. So this is negative 1 to the first power times 1, plus your second term is where k is 2. Negative 1 to the second power times 2. Your third term is where k is 3. Negative 1 to the third power times 3. And that's where you stop because k is going from 1 to 3. So here's where k is 1, k is 2, and k is 3. And this turns out to be negative 1 plus 2 plus a negative 3. Alternating signs, negative, positive, negative. And then this would evaluate out to being what, a negative 2? So you can see this is pretty simple. Suppose you have the summation, k equaling 4 to 5. Now notice your index can start anywhere. Your beginning and ending indices can be whatever numbers, I guess so long as your ending is bigger than your beginning. And suppose this is just k squared. So you put a k value of 4 in, and then you put a k value of 5 in. That's all there is to it. There's just two terms here because your initial value, your initial index was a value of 4. So you put a k of 4, a k of 5, which is 16 plus 25, which is 41.
You start at 4, right?
Right, because it starts you at 4, follow through from 4. Now I'm going to show you just some more stuff in the book. I'm going to pull up the book on page 257, so if you ever wanted to refer this. This is a neat example at the top of the page. It says, express this sum using sigma notation. Sometimes this is not fun, okay? Sometimes this can be, you can get the result fast, and sometimes it's just frustrating. But what is interesting is they show you 1, 2, 3, 4 ways of doing it. So they have 4 different, what I would call formulas, that they can use to generate the sum of those 5 terms. One is start at 0 and go to 4 of 2k plus 1. So when k is 0, it's 1. When k is 1, it's 3. When k is 2, it's 5. So that generates that sequence. Then here's another one. Start at k is 1 and go to 5, but you subtract 1. Here's one you start with k is 2 and go to 6 and you subtract 3. Here you start with k of negative 3 and go to 1. It can be a negative index, and these will all generate that same series. And so you have different formulas that will generate numbers for you. And so you can spend a lot of time playing with these unnecessarily, unless they ask you, and I don't think I put any of that in your homework, so I think it's okay. Here's another interesting fact. When they put this example of k plus k squared, it generates this sum, which could also be rewritten as the summation of the k added to the summation of the k squared. So you can split these, summing the first term and then summing the second term, versus doing it all in one step. And so it's going to lead us to some of these rules that we need to know. And one of these that we use a lot, number 3, we use a lot, which will also grow into integration. It'll be very useful in integration. And then the constant one's kind of interesting too. So the sum and the difference rules, and I will write these down for you, they're really the same except for the addition and the subtraction. So I'm going to combine those into one plus minus formula. But here's some of your formulas, or what they refer to as rules. Rules for finite sums. Finite meaning not infinite, okay, meaning a definite limit to the number of numbers you're adding together. Okay, I should say the number of terms you're having to add together as they're generated by your formulas. But if you have the sum or the difference, really, it is the summation of k equaling 1 to n, where n is some number, of, say, a sub k plus b sub k. Then this is the summation. It can be split up as the summation of the a sub k's plus the summation of the b sub k's. Okay, so you can split it up by doing the first and then adding it to the second. And really, if this was a minus sign, you would do it the minus version. So I'm going to kind of cheat and put both of them into one rule. Then another one is what they call the constant multiple. Okay, and this is where if you have the summation of a constant times your formula or your function, and k is going from, say, 1 to n, then the constant you can pull into the front, like if it's a 5 or a 7, you can pull it in front of the summation. So it's the constant times the summation of k equaling 1 to n of a sub k, something that has the k in the formula. So if it doesn't have k in the formula, then it would be a constant value that you could put in front of your summation or sigma symbol. Then you have the constant value, not the constant multiple, but the constant value, and it's something like this, the summation of k equaling 1 to n of c equaling n times c. Well, an example of this very briefly is if you have the summation of, say, k equaling 1 to 7 of a constant like 5, the number 5. So if you're trying to summation a constant, then this is going to equal 5 times this final ending index, which is 5 times 7, which is 35. Okay, so if it's just a number, you multiply it times that final index to get that result. Okay, so let me do some examples of applying these, which is not difficult. Okay, it's very basic. So 1, 2, 3, I'm going to let this be number 4, being examples. These, like I said, they're not difficult. Suppose they ask me to do the summation of k equaling 1 to n of a negative 5k minus k cubed. Well, you can split this into two parts by making this the summation of a negative 5k, k equaling 1 to n, minus the summation of the k cubed, k equaling 1 to n. Then on this first one, you can bring the negative 5 into the front of the summation. So it's negative 5 times the summation of k equaling 1 to n of k minus the summation of k cubed, k equaling 1 to n. And that's as far as we can go on that one, unless we have some additional rules, which I will show you in just a second. Okay, here's another application. This one's pretty easy. In fact, I'm going to step back and let you... Well, no, I can do it all the way through. This is a 5k plus 7. So using all of these rules, you can split this up as the summation of the 5k plus the summation of the 7 from 1 to 3. Now, since you do have your ending index, you can actually evaluate this. So I'm going to pull the 5 in the front. So this is 5 times the summation of k equaling 1 to 3 of k plus the summation of k equaling 1 to 3 of 7. So this is 5 times k is 1 plus k is 2 plus k is 3. And this one, that's a constant. Yes, but the constant rule said that you can take the number times the maximum value of the index, right, which is 7 plus 7 plus 7. So this is 5 times 6 plus 21, which is 51. So because your index was a number instead of the variable n, you can actually go in and evaluate and get that end result. Now there are some formulas, and these are pretty big deals, okay? This was a lot of work to come up with these formulas. And in the Stewart edition of the calculus book, we had to use these formulas with some extensive work that we did. They're not pushing it. Thomas, this author, is not pushing it. But here's some neat formulas. If you want to take the sum of integers, suppose you want to take the sum of k as k equals 1 to n. So this is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, as many times as you want to add your integers. This is the sum of integers. Again, so this equals 1 plus 2 plus 3 plus 4 plus 5, etc., until you get to plus n on the end. But there is a formula that evaluates this for you, so you don't have to list out the numbers, which is simply n times n plus 1 over 2. So if they said, for example, if they said find the summation of k equaling 1 to 25, which is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 all the way to 25, you can do a shortcut using the formula and say this is 25 times 25 plus 1 divided by 2, which is the sum of all those integers. And it seems simple, but it takes a little while to make that happen. Okay, it takes a little while. What's 25 times 26 divided by 2, which is 25 times 13? 325? Okay. Think about it. If that number was 300, add the first 300 integers. Okay, that's a big, using that formula is nice and handy. All right, another one is the sum of squares. Now these get big. These get big. This formula is the summation of k equaling 1 to n of k squared. So this would be 1 squared plus 2 squared plus 3 squared plus 4 squared, etc., as many as you want to do. Fortunately, there is a formula, and the formula is n times n plus 1 times 2n plus 1 all over 6. So there's a formula that makes that easy for us. So for example, if you wanted to sum up the perfect squares from 1 to 10, it's not very big, right? That's 1 plus 4 plus 9 plus 15 plus 25 plus 36 plus 49, okay, plus 64 plus 81, right? If you want to do it using the formula, n is 10, this would be 10 times 10 plus 1 times 2 times 10 plus 1 all over 6. You have a nice formula. 10 times 11 times 21 over 6. 385. And again, these are not big numbers. So if you chose 100, you could calculate very quickly using this formula. And then one more, this is the sum of cubes. So we're looking at the summation of k cubed from k equaling 1 to n. And that formula is n times n plus 1 over 2, all of this perfectly squared. So they're neat little formulas that are summing up a finite number of cubes. Okay? And they don't push it very hard, but now if you wanted to, which the book is not pushing it, but this example we had up here at this point, the summation of k and the summation of k cubed, we now have these formulas, the summation of k and the summation of k cubed. You could put those in and have a nice formula, and this gives you an n value. You can spit it out very quickly. So those are wonderful shortcuts that took quite a while to derive. Okay. Then we're going to talk here about Mr. Riemann, talking about Riemann sum. The Riemann, okay, this is R-E-I-M-A-N-N, the Riemann sum. Okay, and I'm going to just go to the textbook because it is very well written. And I'm going to look on page 259 and show you what's going on here. Now, Riemann said, we start looking for the area under the curve. Suppose we don't want the width to be consistent of each rectangle under the curve. Okay? Suppose we want it to vary. In this textbook, I didn't mark it up like I did my other textbook. But you can see all this derivation. Okay, let me turn the page. Here it is. It's 261, not 251. Okay, and here's some information over here too. So you can take here we go, I'm sorry, on page 260. We're looking on page 260. Here's a curve. He's finding the area under the curve. This area is going to be negative, and this area is going to be positive unless you take absolute values, which is kind of going back to distance and displacement that we were talking about in the last section. So he takes intervals of different width, and if you look closely, you can see that this one is of much smaller width than this one. Okay, he's varying the width of each one of these rectangles under the curve in order to get higher accuracy. So it says here, on each subinterval, though, to find the area of rectangle, we still form the product, the width times the height. This product may be positive, and it'll be positive above the x-axis, and negative below the x-axis, or even 0, all depending on the sign of the vertical value, the f of x or f of c, of the rectangle, the height of the rectangle. So he comes over here and he sums up all these areas of these rectangles with delta x not being the same for each rectangle. Delta x is varying. This sum is called the Riemann sum. So Riemann's big difference is he doesn't lock the delta x down. He varies the delta x according to what's best for the situation. And then it says, too, in the cases in which the subintervals have equal width, we can make them thinner by simply increasing the number of rectangles, meaning make delta x small. When our partitions have subintervals of varying width, which is what Riemann does, we can ensure that they are all thin by controlling the width of the widest interval. So they're all very small, but the biggest of all the small ones is called the norm. We define the norm of the partition to be the largest of all the subinterval widths. So when they do that, he talks about how that, you can see these images, these rectangles are those of same width or not? No, they're not. They are not of same width at all, okay? So when you partition with the norm approaching 0, when you partition it so that the width of the largest width of all the rectangles is still closing into 0, you get a collection of rectangles that approximate this region with increasing accuracy. So what happens is as we sum the areas of the rectangles, which is where Riemann's coming in, if we make the width increasingly small, we'll convert this to the limit of a function as the width is approaching 0, which will take us into integration. So when we'll move from the summation and this physical, tedious process of finding areas of rectangles under a curve, we'll progress into the summation where you're summing all these rectangles where your width is small, which will take us to the limit where the width is approaching 0, which will then go into integration. So integration is going to turn into finding the area under a curve. So then when you integrate under, then it really goes integration of a velocity curve will tell you distance. And you don't have to draw a whole bunch of rectangles. You just use your methods of integration with all of your shortcuts, and you come up with those values very quickly with great accuracy. So believe it or not, that's all you're going to see in this book. You can see that your homework is going to be very simple in learning the summation. See, the homework looks like this, where you just plug in values. Whoops, move it on the screen. We're just plugging in values and coming up with sums. Very simple stuff, nothing difficult here. I have to get that homework written. I will confess I will have to do it very quickly when I go back to my office. But we've covered section 5.1 and 5.2 today. You have homework only in one at the moment, but I will get both of them up. Y'all enjoy the rest of your afternoon now that the sun is shining again. So until we meet again.